Welcome to ROStudio. ROStudio is a tool that enables a bottom-up approach to abstracting common parts of scenarios and generate new variations by annotating an existing code base. In this demo, we will introduce the ROStudio user interface and illustrate its basic concepts using an example from the robotics domain. Let's first look at some of the basic elements of the UI. From the start page that you are looking at here, it is evident that we have developed ROStudio especially for our domain of robotics inside SAP, and in particular to support scenarios that connect robotics systems with SAP backend systems. As we will see later, ROStudio is by far not restricted to that domain, but we have focused on it in this first version. If we click on SAP Backend Systems, we see a list of entries representing SAP systems and environments that we have used so far in our scenarios. The collection of those entries can be seen as a kind of registry that can be accessed when working on connection scenarios, as we will see later. Let's have a look at one of those entries. We can see here a collection of entries of key-value pairs that represent information about that specific system. The list of key-value pairs is by far not a complete description of all possible attributes or properties of this system, but rather a collection of fields that are or will be relevant for a connection scenario. Only few of those fields are built in, like name, description, created, and modified timestamps. The other fields have been added from with the UI, as we will see next. In this case we have information about host, user, password, etc. We can also add code snippets that are specific for the particular entry, as we can see in the Demo Objects field. If we want to add a new or remove an existing field for this registry, we can use the corresponding entry in the Metadata drop-down. Let's add a new field to our backend systems registry. Let's say we need a new field named Client. We can now type in the name, select the type, in this case, string, and click Add New Field. You can see in the drop-down that you can use different kinds of value types including integer, double, boolean, and source code. The latter can hold the code snippets, as mentioned earlier. We can now use the new field in any of our entries, for instance in this one. In order to change the value, we switch to Edit mode and enter values as needed, including for the newly created field Client. Any of the user-defined fields can be removed as well, using the corresponding Remove a Field entry in the Metadata drop-down. Analogously, we have built up a registry of robots and robotics systems. Let's have a look at a few entries that we will also use in our demo later. Here we see our entry for the Fetch Freight robot. Besides more informative fields like name, description, website, manufacturer, has fields that we will actually use in this demo, short name, and robot category. As we see here, the short name is Fetch Freight and the category is logistics. Let's have a look at another entry, say the Fetch Mobile Manipulator. Here you see, the robot category is different, as this particular robot is also able to perform pick and place tasks. We will now get to the main part of the demo by showing how we can use scenario classes and their instances to quickly create different variations of similar software packages that share the majority of the code, but still need to be kept separate for various technical or non-technical reasons. As we want to show an example from the robotics domain, and a real-life demo would be too much overhead to show here, we will demonstrate the capabilities of ROStudio using the next best thing, a simulated robot scenario. As starting point, we are using a ROS environment with the simulator tool, Gazebo, that runs the Fetch Robotics simulation demo, the code of which is available on the Fetch Robotics website. As our baseline, we will first have a look at the original scenario, and will later show how we use ROStudio to generate different variations of it. We therefore switch to our ROS Ubuntu virtual machine and run the original Fetch Gazebo demo. As we can see, we have a Fetch mobile manipulator robot in the simulated world, as well as 2 cafe tables. The task of the robot is to move to the first table, pick up the little box and place it on the second table. Let's assume now, we use this as our base scenario, or, expressed in a simplified way, a robot moving to different places in different environments and moving objects between those places. For instance, we have customer A who has robot system X, and now we want to use the same code for a different customer B who has robot system Y and a different setup, but without copying or refactoring code. We will now show how this is done using the ROSstudio metaprogramming and source-to-source code generation techniques. In this case, we are starting from an existing code base, namely the code that is provided by the Fetch Robotics company for the demo we just saw. ROSstudio has an integrated GitHub access, so we have put the demo code into a project in github.com, as we can see here. Let's now go back to ROSstudio and open the Connection Scenario page. If we would start from scratch, we would create a new connection scenario project, or class, as we will refer to it in this demo, and use the untouched code from the original Fetch demo as starting point. For demo purposes, we have prepared such a project beforehand and called in Gazebo Demo. We have linked our demo code from the Git repository with this scenario class as we can see here. Below that we have the section for placeholders. Each placeholder in a scenario class represents a meta variable, which can later be instantiated with a concrete object from the ROSstudio registry. As ROSstudio currently has registries for backend systems and robotic systems, we can add corresponding placeholders here, depending on the particular needs of the scenario. As our scenario only deals with one robotic system, we only use this one placeholder here. We can see here the placeholder definition. In this case, it just consists of an identifier and a description string. The identifier is what is used in the code templates to refer to this placeholder. We could have added additional constraints to this placeholder, for instance, what types of robots are allowed for this scenario, but we have skipped this for brevity here. We will now turn our attention to the core functionality of ROSstudio, the generation of scenario instances using metaprogramming techniques. For that, we will switch to the Code Template tab in our scenario class. What we see here is a view into the GitHub repository that we have linked with this scenario. ROSstudio has a fully functional Git client that enables code changes, commits, and refresh operations from the GitHub repository. We will now show how we can turn this collection of code files into an artifact that can be used to generate different variations by gradually adding what we call variation points in those code files. Variation points are those places in the code that make up the differences between the different variants for the scenario. The idea is to annotate the code in such a way that by manipulating a few configuration parameters, different variations of the scenario can be generated on the fly that otherwise would require synchronized code changes at potentially many different places in the code. Let's take a look how this could look like in our demo scenario. First, we will take a look at the file that contains the objects that appear in the simulator when the demo starts up. We see, for instance, the 2 cafe tables, and the box, here called Demo Cube, being placed on top of the first table, as you can see by looking at the coordinates of the objects. Now, let's go back to our fictitious situation, where we have different customers and we need to quickly come up with customized packages to be deployed for the respective scenario. Let's assume we want to add certain objects into the worlds, change the position of those tables, and have different robots. For that reason, I have created an annotated version of that same file. I could have actually used the original file, but for demo purposes I have created a new one. You can see here lines and expressions that usually don't fit into this kind of XML file, namely directive lines starting with // and inline expressions of the form $$ followed by an expression in curly brackets. Those are the annotations used by the ROSstudio code generator, and by carefully analyzing them, you might guess what their purpose is in this case. Let's, for instance, look at the highlighted annotated code snippet. It controls whether the XML include construct in between the directive lines is generated in the resulting code or not, and the condition refers to a field called world.includeWalls. But where does that field come from? The answer to that can be found in the Config Template tab, that we can bring up here. Along with the annotated code files, the config template represents the core piece of ROS Studio's code generation. In here, we define the configuration parameters that make up the differences between the variations of our scenario. This is the place where configuration parameters like world.includeWalls are defined and get their default values. When we, in the next step, create instances of our scenario, we can manipulate this and other configuration parameters to cater to the specific requirements of the scenario variant. Let's take a closer look at the definition of the cafe tables in the configuration. As you can see, the cafe tables are given as a list of elements with a name, a pose specifying their position in the simulated world, and information about whether the box, cube, is sitting on a particular table or not. Additionally, the table, which is supposed to eventually receive the box, will have the Boolean flag, ESPLOSATarget, set to true. Now, let's go back to the world definition file and check out the place in the code that introduced the cafe tables. This is an example of a more elaborate annotation, as we are using a meta for each loop to generate the XML constructs for each of the tables. The inline expressions, for instance ctable.name, are used to put in the values at the right places in the code. In addition, the hasCube flag controls the placement of the box onto that particular table by positioning it slightly off-center of the table. This all is expressed by ROS Studio's meta-programming constructs, which use JavaScript as underlying engine. We will now get to the key part of what ROS Studio can do, the generation of variants, in our case the robot simulation demo. For that, we need to create what we call instances of our scenario class. We go back to the Settings tab and click on Create Instance in the top. We have now created an instance of our scenario class. We will give it the name Customer A Instance and click Save. We have now created of what seems to be a copy of our scenario class, but with one decisive difference: all the code files in this instance object are created using the ROS Studio code generator and the configuration that is associated with this very instance object. Let's now start to customize our instance, so that it becomes an instance of our scenario class that is tailored to the needs of our fictitious customer A. Say, this customer is using the fetch freight base as robot. In order to express that, we can now make use of the placeholder that we have defined in our scenario class. We are going to instantiate that placeholder now by a simple drag and drop operation in the UI like it is shown here. Once this is done, the UI visually indicates that this placeholder is now instantiated with this robot. If we would have put constraints on the placeholder during its definition and we would have tried to drag a robot onto the tile for which the constraints would not have been met, ROS Studio would have rejected the instantiation operation. Let's now take a look at the Config tab. This is the other place where we perform the customization of this instance object. Because we have just created this instance object, the content of this config has been copied from the scenario class with all the default values defined there. We can now go ahead and perform further customizations. For instance, let's change the color of that little box to red. Next, we want to have the walls included in this scenario, so we change the corresponding parameter to true. Before performing more changes, we should take a look at the code base and how our changes have affected what has been generated. As you can see, the tab title now says Instantiated Code, indicating the fact that we are looking at code that has been generated from the scenario class code templates. We will now open the exact same path as we did in the scenario class: ROS packages, myFetchGazebo, worlds, myTestZone.sdf. Here, for example, directive lines starting with // exclamation mark, but just plain source code, in this case XML. We further see that the includes section for the walls is now contained in the code. RoseStudio has further generated the cafe table objects by executing the meta loop contained in the code template file, and has put the demo cube onto the table using the hasCube flag, as we can see here. Of course, the changes in the codebase are not limited to this one file, otherwise the benefits of our approach wouldn't be that great. Many of the changes are spread over several code files. One change in the config can have an impact on as many different places in the code, where the change would have an impact. Before we get further into how the code generation works, we will get to the next step in the RoseStudio workflow, the deployment of the generated code for our instantiated variant for customer A. For that, we will create a customized, deployable artifact that can directly be used, for XMaple at the customer site, to install and deploy the customized package. RoseStudio therefore has the functionality to create a zip archive file for the instantiated code, which will be downloaded on the local machine. Let's do that now. Depending on the browser and your browser settings, this file is now downloaded to a local directory, in this case our downloads folder. We will now run the code that we have just downloaded. For that I have prepared a script that takes the latest zip file from my downloads directory, unpacks it and run the demo script. We can now see that the things we have configured are reflected in this setup. The robot is now a fetch freight, the walls are in the scene and the little box has changed its color to red. We can start the movement of the robot by hitting enter in this terminal window. We can see that the robot starts moving towards the first table. The box is now placed on top of the robot and it starts moving towards the second table to deliver it. While this simulation is running in the background, we will go back to RoseStudio and take one more look at the code. I wanted to show how changing the position and number of cafe tables not impacted the XML file we looked at earlier, but also the actual Python script that controls the movement of the robot in the demo. We therefore open that script, first in our instantiated code base, by going to Rose Packages, myFetch Gazebo Demo, mydemo.py. If we navigate to the main program, we can see the instructions to move the robot between the tables as well as instructions to place the box onto robot and destination table. Now, as you might recall, we have the positioning and the number of tables specified in our config, so that this very piece of code is highly dependent on whatever we have put in our config. In order to highlight that, we will now go up to the corresponding file in our scenario class, which we can quickly do by clicking on Go to Template File in this screen. Now, here you can see the meta-programming constructs that are embedded into the original code, and especially the meta loop that iterates over the cafe table objects defined in the config and how the values of the coordinates, for example, are inserted at the appropriate places in the code. If we would have specified 10 cafe tables in the configuration of our customer instance, this for loop would have created the code to place all those tables into the scene of the simulated world with the corresponding coordinates that we would have specified for them. This is just an example on how a small change in the config impacts the code at many different places. Managing those changes manually would be much more effort and eventually become a maintenance nightmare when too many of those variations need to be kept separate and reproducible. Finally, we want to create a second variant for another customer B, who has a different setup. For that, we go back to the Settings tab of our scenario class and create a new instance like we did before for customer A. We go through the same steps as in the first case. Now we name it Customer B Instance, and click Save. We have now created a new variant for this customer, who doesn't have the fetch robot, but the Mir robot on site. We therefore drag the Mir robot from our registry onto the placeholder. Now, we want to modify the config a little further, and, for instance, include a dumpster in the scenery. We further want to add another cafe table, and make it the delivery target for the box. The new table will get coordinates 5 and -3, so it will be towards the front left in our simulation scene. We now perform the same steps for deploying this code variation as we did before for our customer, A variant. We create a new zip file, wait until it is downloaded and start the demo script from the command line. As expected, we will see the changed setup. The robot is now Mir, and the third table is inserted in the simulated world. I hope this demo gave you an idea of how ROSstudio is able to support the development of different variations of similar scenarios. Keep in mind that we could only touch on some basic principles in this demo for obvious reasons, but it hopefully already became clear that even with small variations you can easily lose track of all the changes that have to be made to accomplish those modifications without the support provided by ROSstudio. By adding more and more variation points in your code, you can expand the set of applicable scenarios to a point that your configuration becomes the abstract representation of your solution, which explains my initial remarks about ROS supporting a so-called bottom-up abstraction approach. Thank you for your attention.